On Tuesday, we learned to calculate equilibrium concentrations from one equilibrium concentration, initial concentrations, and the K, equilibrium constant. And we ended up using a solver because we had quadratic equations, and some of you probably felt like, man, this is kind of gnarly math. I don't know about this. That's okay. Sometimes we have to use a solver or a quadratic equation or some other kind of difficult way to solve these problems. Other times we can make simplifying assumptions that end up with the equation just having some simple algebra in it. So sometimes we can simplify by making these approximations. So when can we do this? Well, if the equilibrium constant is small, that means that the reaction does not go very far towards the products. So the change in reactant concentration is going to be small. If that change is small relative to the concentrations, so if the initial reactant concentration is fairly large and X is small in comparison, then essentially the reactant concentrations do not change. And so then that simplifies the equation. Well, when can we do this? We can do this if the calculated value of X is 5% or less than the number it's subtracted from. Now, it may bother you that we'll start with a concentration and we'll subtract some and we'll say, well, it's the same. It didn't change. Does that bother anybody? It seems wrong, yeah? Okay, so I live in Reedley, fruit basket of the world. There's nuts too. There's trucks everywhere because packing houses, right? And so it's not uncommon to see multiple trucks like loaded with peaches driving through town. And so they need to weigh the truck before and after they get the load to see what the load is, etc. So let's say the truck full of peaches pulls up onto the scale and the weight of the truck is recorded. And then as they're driving away, one of the peaches falls out of the truck. Do they need to go back and weigh the truck again? No, because the truck with the peaches in it is thousands and thousands of pounds, right? And the peach is just a few ounces. It just doesn't make a difference, right? It's like a drop of water in your swimming pool. Well, has the volume changed? Well, technically, yes. Can you measure the change in volume? Probably not, right? So what we're talking about here is the amount of reactant that reacts is like that peach that falls off the loaded truck. It is so small that subtracting it from the initial concentration, we can't tell the difference, okay? So let's look at how this might work. Simple equation here. A goes to 2B. Here's our equilibrium constant. 3.3 times 10 to the minus 5. So this is a fairly small number. We've got initial concentration of A being 1 molar and B being 0 molar. And just to give you an idea of what do we mean by a large concentration, 1 molar is actually a very large concentration for most of the things that we see. Even like 0.1 molar is still fairly large, okay? 0.00001 molar would be considered small, okay? So this is a large concentration. This is a small equilibrium constant. We're going to follow the same steps that we learned on Tuesday. We're going to make our ice table. We're going to put in the initial concentrations that we know. And then we're going to look at the change. So A goes down by X, because it has a coefficient of 1. And B goes up by 2X, because it has a coefficient of 2. Okay? This is partly why I like to use the chemical equation as the header, because then you've got that coefficient right there, you can't miss it. So this 2 is why we have a 2 here. So then we add the initial and change rows to get the equilibrium row. So 1 plus negative x is 1 minus x. 0 plus 2x is 2x. Then we write the equilibrium constant expression based on the chemical equation. So for this one, it's products over reactants. So we've got B, and that's going to be squared because of the coefficient, divided by the concentration of A. The next step that we did is we've got K and we've got expressions for the equilibrium concentrations. So we're going to plug all of those into our equation. So 3.3 times 10 to the minus 5 is equal to the concentration of B, which is 2x squared, divided by the concentration of A, 1.0 minus x. What we did on Tuesday is then we took this and we plugged it into our solver and we solved for x, right? I'm going to do that real quick. Let's see, number solver. Number solver's very busy right now. Getting a lot of use. So the solver gives x is equal to 0.002868. Just, if I'm going to make a mistake in writing sig figs, I want to write too many rather than not enough. Okay, so that's using the solver. What about this approximation? Large initial concentration, small equilibrium constant. So the x's small approximation says, well, this change is like the peach that fell off the truck. It doesn't really matter. So then 1 minus this is still 1. Okay, so we're saying here that that x is so small we can call it 0. Doesn't matter. Is this x also 0 then? No, because this isn't being added to or subtracted from anything. This is, you were walking on the sidewalk and you picked up this peach. How much does it weigh? Well, you're not going to use the truck scale, right? You're going to use maybe a kitchen scale, and you could find out, oh, it weighs 6 ounces or whatever. So this x is not 0. This x isn't 0 either. It is just so small, we can pretend it's 0. Okay? So let's use a different color here. So now we can rewrite this 3.3 times 10 to the minus 5 is equal to 2x squared divided by 1. Oh, well, that's simpler, isn't it? Right? So the right side here is equivalent to 4x squared. So I'm going to divide both sides by 4. X squared is 3.3 times 10 to the minus 5 divided by 4. And then I'm going to take the square root of both sides. And if algebra is not your friend, you can also use the solver to solve this one. That's fine. So then what I've got is the square root of 3.3 times 10 to the minus 5 divided by 4. So this tells me that x is equal to 0.00, kind of messy, 2872. Are those x's close to each other? 0.002868, 0.002872. Yeah, those are really close. So the check to see that the X's small approximation is valid without doing the other calculation is we're going to take what we get for X and we're going to find out what percent of this number is it, whatever I'm subtracting it or adding it to. So 0.002872 divided by what I'm subtracting it from times 100 gives me 0.00, 0.2872%, which is definitely less than 5%. Okay, so the X's small approximation works. What are the equilibrium concentrations? Well, I'm going to do this up on the top because I ran out of room down there. Well, the concentration of A is 1 minus X. Now, we said X was so small it didn't matter. Let's prove it to ourselves. So this is 1.0 minus 0.002872. So I do that on my calculator. And it gives me 0.997128. What's a reasonable number of significant figures for that concentration? 2? Yeah. Or technically, really, 1 decimal place, right? Because this is an uncertain digit. So if I round this to 1 decimal place, what do I get? 1. I'm going to keep this first 9, and the next 9 tells me I have to round it up, and I end up with 1.0. It didn't affect it. Okay? And then the concentration of B is 2 times X. So 0.002872 times 2. Is that right? 0.005744. And we want to consider sig figs, but we don't want to think too hard about it. Okay? So this has 2 sig figs. That has 2 sig figs. This has 2 sig figs. 2 is probably good, right? So we'll call this 0.0057 molar. And this one was 1 molar. You okay with that? It is a little disturbing because how could you take some away and have it be the same number? But just remember the peach falling off the loaded truck. It's so small in comparison, it doesn't matter at all. Okay, let's do a more real example. Here's an actual chemical reaction. H2S decomposing into hydrogen and sulfur. Here's our equilibrium constant, 1.67 times 10 to the minus 7, so that's nice and small. At 800 degrees, why are they telling us that? Because this is the constant at that particular temperature, and we can use it if the reaction is at that temperature, right? And the reaction is at that temperature. I'm not going to try to trick you by giving you one temperature for the equilibrium constant and then telling you the reaction is happening at another one. But I just don't want you to be confused by why that's in there. We don't have to do anything with it, okay? So here we have a reaction mixture where we have 0.1 molar of the reactant and 0.1 molar of one of the products and none of the other product. We're supposed to find the equilibrium concentration of S2. So we're going to make an ice table. So for all these equilibrium problems, ice table is the first thing we do. Again, I like to use the balanced chemical equation has the header, because then it's got the coefficients in there, and it's less confusing. So there's that. And I'm going to make my, oops, that's not what I wanted to do. So I'm going to try using a different color here. ICE, ice table. Okay? Let's put in the initial concentrations that we were given. So we're told that the H2S was 0.1 molar. And that is a small number, but in terms of concentrations, it's actually fairly large. And the concentration of the H2 is 0.1 molar. And the concentration of S2 initially is 0.00. Now we say, well, how are these going to change? So we've got this double line here where the reaction arrow is. I've got two things on the right side. They're both going to be plus X or they're both going to be minus X, because the reaction is either going to go to the forward direction or to the reverse direction. We can't have this one go down and that one go up. Not possible. Okay? So how do we know which direction it's going to go? Well, most of the time we can just use a little bit of common sense. If we're starting out with 0 of that, can it go down? We can't get smaller than 0. So this has to go up. So that's going to go up by X. There's no coefficient in front of the S2, and so I'm not going to multiply the X by anything. So that one goes up. That means this one also goes up. But that one does have a 2 in front of it. So this coefficient of 2 is why I'm writing 2x here. Okay? So this side went up. That means the other side has to go down. So this will be negative. And again, we're going to use the coefficient. We're using the stoichiometry. Minus 2x. So now we'll take our I and our C and add them together to get E. 0.100 minus 2x. 0.100 plus 2x. And just x, because 0 plus x is x. I'm going to write the equilibrium constant expression from the chemical equation. You should always show work when you do these. I would not try to do this in my head. And I teach this for a living, right? If I wouldn't try to do this in my head, you shouldn't try to do it in your head either. So we're going to make the ice table. We're going to write out the equilibrium expression. We're going to take these guys and plug them in. At that point, if you want to just use your calculator or rearrange things in your head, fine. Absolutely, you can do that. But up to this point, we need to write this stuff down. So Kc is 1.67 times 10 to the minus 7. And that's equal to the hydrogen concentration at equilibrium, and that's squared, times the sulfur concentration, which was just X. And this is divided by the H2S concentration. which is 0.1 minus 2x. Okay? You can always use the solver and find the answer. In my book, that's never wrong. But we're practicing the x is small approximation. We have a small equilibrium constant. We have relatively large initial concentrations. We're going to say, well, maybe x is so small that subtracting it or adding it to these concentrations is not going to affect it. Because, again, with the peach truck, right? If you toss 2 peaches up there, is that going to change the mass of the truck? Not in a way that you can detect it. So we're going to say, well, I think this is so small that that is essentially 0. And this one is so small that that's 0. Bless you. Anywhere you're adding or subtracting the x, it will go to 0. If it's by itself or multiplied by something, we're going to keep it. So this initial concentration is like the loaded truck, and adding or subtracting however many x's is a few peaches, one way or the other. So now what do we have? We just have x, right? This is 0.1 squared divided by 0.1 squared. Those cancel out. How convenient. So we end up with x is equal to 1.67 times 10 to the minus 2. That'd be a molar. So that was easier, right? It's almost no algebra. We should always check the approximation. And we do that by taking our x and dividing it by the initial concentration, which, what we're subtracting it from. Oh, I put the wrong concentration. 0.100. That's a good question. Does it matter which one we use? Here it doesn't, because they are the same. If one of these is larger than the other, I want to use the smallest one because that's where the percentage is likely to be the biggest, right? So if this number was much smaller, it might make a difference subtracting from this one. You know, maybe a kid brings his toy semi-truck, right? And one peach falls off of that. Well, because it's so much smaller to start with, it matters, right? So we're going to look at whichever thing is smaller. It's what we're adding or subtracting from. That's okay. So I should do this in my head, but I don't trust myself this morning. Is that less than 5? Heck yeah. So the S2 concentration at equilibrium is 1.67 times 10 to the minus 7 molar. That is a small concentration. But with modern analytical chemistry techniques, we can detect concentrations even smaller than that. Yeah. Let's, just for grins, see what the solver would say. If you came in late, there's TI-36X pros up here that you're welcome to borrow. So 0.1 plus 2x quantity squared times x divided by 0.1 minus 2x quantity squared. So from the solver, I'm getting 1.669977 times 10 to the minus 7. Is that different at all? No, it isn't. Any questions? So, some instructors don't like you to use a solver. They want you to use a quadratic formula. I think that's cruel and unusual punishment. But I also don't want to force everyone to learn how to use the solver. So typically on exams, you can use the x is small approximation to solve things like this. We're not going to make you use a solver or the quadratic equation on an exam. Okay, so this one looks the same, doesn't it? What's different? The concentrations, the initial concentrations. This time we're starting with H2S 1 times 10 to the minus 4 instead of 0.1, and hydrogen is 0 instead of 0.1. Oops. So call that cheating if you want. I call that being efficient. Ice table. Put in the initial concentrations. 1.00 times 10 to the minus 4. 0.00, 0.00. We have no products, so these can only go up. So the positive x's are on this side, on the product side. The negative is on the reactant side. That is not always the case. Sometimes the negative will be over here and the positive's over there. Excuse me. So we add these together, and then this one ends up getting a little squished. But we can do it. I should have copied this too. Made a little mistake there, but I recovered. Okay, equilibrium constant expression. Plug the numbers in, the values. So 1.67 times 10 to the minus 7 is equal to 2x, the quantity squared, that's this guy right here, times x, divided by 1.00 times 10 to the minus 4 minus 2x, the quantity squared. we really have to pay attention to these these coefficients that aren't 1, because they're going to show up in the change, and they're also going to show up in the equilibrium expression. So if you leave those out, it's not going to work out very well. Let's try the x is small approximation, because we learned how to do that, and that was really easy last time. So let's assume that that's going to go to 0. So this is not as simple as that first one, but it's still much more simple. So I'm going to take 2x, the quantity squared, that's 4x squared, times x. So this side is 4x cubed. And the other side is going to be 1.67 times 10 to the minus 4 times 1.00. I did that again. That's not minus 4, it's minus 7. Did that yesterday too. Minus 7. This one's times 10 to the minus 4 squared. Did I do that right? So I could divide that by 4. So the 4's go away. And then I'm going to take the cube root to make the x cubed go away. Again, if you don't like algebra, you can simplify here and plug it into the solver, or you can just plug the whole thing into the solver. You'll come up with a good answer either way. So I've got the cube root of 1.67 times 10 to the minus 7. Oops. Minus 7 times 1 times 10 to the minus 4 divided by 4. .13 times 10 to the minus 6. That's pretty small, right? How do we check to see if it's valid? We're going to divide it by what it was subtracted from to see if it's 5% or less. So 6.13 times 10 to the minus 6 divided by what I subtracted it from. Different than it was yesterday. What am I doing? Getting 6.3? Anybody else? Yesterday I thought it was 7.5. 7.5?
Yeah.
What am I doing wrong? Did you get this number the same, 6.13 times 10 to the minus 4? Anybody? Yes, no, maybe so. Not going to help me out? Okay, I'll do it again. Getting the same number. .3%. That 5 or less? No, it isn't. The approximation is not valid. We do need to use the solver. Mm-hmm. Okay. Yeah, I'm wondering what, because I thought I remembered having a 7.5% error. Okay, good. I will go back to that in a second. Um, the solver is giving me x equals 6.78 times 10 to the negative 6. Okay. I'm going to go back and see what I was doing wrong. Cube root. Oh, I know what I forgot. I forgot the squared here. Well, this is the answer, yes. But this is the wrong answer. Well, I did it wrong. Your answer is correct. The 7.5, that's correct. I forgot to square this. Turns out that makes a difference. Who knew? I did. Okay, I'm going to pause because something, I don't know what's going on. Okay, I cannot see what I'm doing wrong right now, but I am doing something wrong when I'm doing this math. And Ethan got the answer that is actually correct. And that answer is 7.47 times 10 to the minus 6. Oh, 7.5%. That's what you get to? Yeah. So after class, I'll go back and argue with my calculator. I don't know what I was doing. I thought I found the mistake, and then it wasn't the mistake. Who knows? Right. So 6.78 times 10 to the minus 6. So that is x, and S2 is what we were finding, and the S2 is equal to x. So x is not always the answer, but sometimes it is. Questions? That went much better yesterday. Okay. For the generic reaction A goes to B, consider each value of K an initial concentration of A. For which set of values does the X is small approximation most likely apply? Are we looking for large K or small K?
No, small K.
Small K. Small K because we don't want it to go very far. That means that X is going to be small. So we've got two choices here, 10 to the minus 5 and 10 to the minus 2. So X is, when K is small, it's more likely to be true. So we'll get rid of those. And then, do we want the concentration to be large or small? We want it to be large. So A is where it's most likely to be true. Any questions? just some notes here. Concentrations have to be in moles per liter. I don't know that I've ever put a question on an exam where I tried to trick you with that, but there's probably some in the homework. In fact, yesterday I was helping somebody and it gave them a volume for the solution and the moles of reactants and stuff. And then they had to do a problem. Well, you can't use the moles. It has to be the molarity. So for that one, you had to calculate the molarities first and then do it. We need to use the appropriate equilibrium constant. If we're using pressures, it's got to be Kp. If it's using concentration, it has to be Kc. Now, this is one you're more likely to see as a trick on an exam. There's a relationship between these, right? It's given on the useful information sheet, right? I have a hard time remembering it too. It's like, is Kp equal to Kc times the thing, or is it the other way around? But there's an equation. So if you're given a bunch of pressures, but you're given Kc, you need to change this into Kp before you do the problem. This one, I kind of feel like not even telling you. Sometimes you can use moles instead of molarity. The only time, though, is when the moles of reactants in the chemical equation is equal to the moles of products. So I think it's best to pretend that you can't do that. Just always use molarity. And then another thing important to remember, the x is small approximation does not mean that x is 0. It means this other number minus x is so small it didn't change. Okay?